In the previous video, we finally finished the last two circuits in our quest to understand and breadboard the entire Breakout Arcade game. Next up on the project plan is to start designing the circuit board, but we did say we'd look to see if we could possibly support VGA, so this video is a short excursion to check that out. If you look at the specs, VGA requires around double the horizontal rate that we produce, and our other timings in general are a bit funky. VGA also requires analog RGB signals, so we would need to convert our various UI elements to analog voltages. We're not looking to make changes to the original Breakout design either, so an optional add-on for more advanced video would be best. While researching this on the interweb, I ran across this open source project, RGB to HDMI, that can give us HDMI support without a lot of work, and lazy is good. It's fine that we get some help with this anyway because our main focus is Breakout. The RGB to HDMI project was born from a desire to connect retro computers to modern displays. It has two main components, a custom application that runs on a Raspberry Pi Zero to drive the HDMI output, and a CPLD daughter board to sample source video. The latest versions can handle 12-bit TTL RGB signals, and there's even an add-on interface to accept RGB analog video. RGB to HDMI is open source and everything is available online. You can buy pre-assembled boards or throw the Gerbers at your favorite fab and build your own. I just wanted to get something going, so I ordered mine. I also ordered an optional HDMI audio support board, and I ordered a couple Zeros. As you know, the original Breakout emits black and white composite video, and color is achieved via cellophane strips stuck directly to the monitor face. RGB to HDMI will let us add color, but we still need to do a bit of work to bring out our UI elements and convert those to the proper color signals. Since our palette is simple, we can get away with just 6-bit RGB. First thing I did was to map our UI elements to target colors that are close to the originals using hex color codes. 2 bits per color gives us 4 brightness levels for each. To get short hex codes, we simply double up the bits. To get long hex codes, we double that. And we can look these up in standard color tables. I don't want to make any changes from the original colors, but I would like to make the borders a little darker to mimic behavior I've seen in many instances where the score seems a little brighter than the borders. While waiting for that stuff to arrive, I created logic to generate the proper color bits from our mappings. Yeah, I know Wozniak could have done this in half a transistor, but I don't have any alien blood, so this is what you get. I'm not sure if you've used Logisim before, but it is another great free tool you can use to prototype circuits. Our mapper circuit is on the left, and the stuff on the right is just to test the output. Inputs are all signals from Breakout, and the outputs drive the capture daughter card. You know where all of these inputs come from our various breadboarding videos, except for the not boundary line, which comes from here. I'll start with all Breakout signals off, which emits all zeros or black. Turn on the ball or score, and we get white. Turn on the boundaries, and there's that gray. Paddle correctly emits blue. Turn on brick display. We get red when both H16 and H8 are off because it's the closest to the top boundary. Next row should be orange, then green, then yellow. That's working nominally, so we can throw it on a breadboard. I have 5 chips on the breadboard because I wanted some extra buffering, but we can do this in 4. We could put this mapper circuit directly onto the retro board by consuming unused gates in the 3 empty sites, but I think it best that we add this circuitry off-board and just bring the required signals to a connector on the retro. This will allow us to use RGB to HDMI, or give the flexibility to roll something else. One last note is that we can power this stack directly from the retro, so we should make VCC available on the connector as a jumperable option. One thing I don't know yet is how RGB to HDMI handles invisible pixels stepping on sync signals, and you know from the various circuits there's a lot of mischief in the original design. If there are issues, we'll need to add a bit more logic to keep visible stuff out of the syncs, but we'll see. Those parts just arrived, so let's put this together. The CPLD board already has a header socket installed, so I just needed to solder a strip header to the Pi and sandwich them together. The source feed connector is between the boards, so I had to plug in a ribbon cable first, then hook that to my breadboard. The code load is simple. Just unzip and copy the distribution file contents to the root of a FAT formatted SD card. It only requires a few gigabytes, so you can go small. Settings are done via these 3 buttons and on-screen menus. Pop in that SD card and connect a mini HDMI cable to my monitor. I'm just going to wire up the syncs and scoreline for now. Since the scoreline is the only UI element that doesn't encroach on the syncs, it should be a good starting point. Fire that up. Cool. We got something already. I scrolled through a bunch of pre-built profiles. The TRS-80 Model 4 was the most stable, but it's not exactly correct. I'll plug in the boundary line next to get a good outline of the visual space. Well, it didn't crap itself, so I'm thinking she ignores visual pixel data received inside the syncs. Great for us as we can go cheap on the logic, but we are missing the right-hand boundary. If you remember from the border circuitry, the right-hand boundary sits inside the end of VSync, or VSync sits inside the end of the boundary. We therefore need to turn off VSync before it hits the right-hand side. Nothing fancy is actually needed. We can simply block VSync using a boundary signal with a one-wire change. Try that out, and the right-hand boundary starts to appear. Since our geometry is a bit strange, let's create a custom profile with our exact numbers. I'll set the pixel width to 256, the pixel height to 252, and the line length to 256. After that, you can see the derived clock is pretty close to our 4.09 MHz pixel clock. I'll hit Auto Calibrate Video Sampling next to have it analyze the best phase to use for our pixel data. This function works by sampling our video at various phases of our pixel clock to see which one gives the fewest errors. Looks pretty stable now. This doesn't fill the screen, but we can adjust scaling. Switch to Interpolate Full, and it fills the target screen space. Go back to the sampling menu and shift this to the right a bit by increasing the pixel H offset value. Let's add in some more UI elements. Hook up the paddle, and nothing. Turns out that the palette was set to 2-level mono. Just needed to set it to RGB. The blue bar looks pretty nice, and it's our first color element. Add the brick signal. They're all there. Hook in H8 and H16. Looks amazing, but those 5-point bricks are supposed to be orange. In the palette menu, we didn't go far enough. We needed to go all the way to EGA. Now that's awesome. Last signal is a ball, but we won't see that until we start a game. That looks pretty good, and I'm sure we can make more adjustments to improve it. If you are an expert on these, let me know if I have a serious case of the dumbass here. Wow, so much better than black and white. A quick test for flip screen. That's not correct. I went back to the sampling menu and redid the auto calibrate. Looks fine now, and the regular screen looks good too. The only thing missing now is audio. This HDMI audio support board gets soldered directly on top of the daughter board. We also need to solder audio into these pads. I have a spare RCA cable and connector from the monitor test fixture we built. This has both channels, but we can configure the board to only use one input for mono. Try that out. Works like a charm. Amazing. Well, now we have a reasonable solution for advanced video, and we didn't have to do much work. If you really want VGA, you can either roll your own or drop a cheap HDMI to VGA adapter on top of this. No need to dive any deeper right now because the series is not about this, but at least we know we can bring out and abuse our UI signals. We will make sure to add a connector for the UI elements to the retro board, and we will do a small mapper board specifically to support RGB to HDMI. I've got to go play around with this a bit. See you in the next part, and thanks for watching.